Okay, so the last video cut me off. I've got that 15-minute maximum limit on my videos with the screen capture software I'm using. Just as we were calculating the required moment of inertia, we need, in order to not exceed our maximum allowable deflection, to have a moment of inertia of 1,429 inches to the fourth. And we have chosen a W12 by 62, which has a moment of inertia of 1330 inches to the fourth. So that's bad news. That means that the beam that we chose is not going to be stiff enough. It's going to deflect too much, and therefore we have to go back to the drawing board, essentially. So we need to go back and look in the appendix for a beam that does provide us a moment of inertia of at least 1429. Now, just like there's an appendix that lists wide flange beams in order of ZX, there is also a separate appendix which lists wide flange beams in order of their IX value, their moment of inertia. Let's take a look and see which appendix that is. So the appendix that lists the wide flange beams in order of their moment of inertia is Appendix J. And according to Appendix J, if we were to choose a W21 by 73, we would have a plastic section modulus of 172. That's still going to be good. In fact, that's even better. That's comparing that to the 128 that we need. We needed 128. This provides 172, so we're good on that front. And the moment of inertia, I sub x, for W21 by 73 is 1600 inches to the fourth. Compare that to the required 1429, and that's good. Now, technically, this adds some additional self-weight. We've gone from 62 pounds per foot to 73 pounds per foot. So that's an additional 11 pounds per foot. But as you can see, when we went back and calculated the additional section modulus, plastic section modulus required by our additional self-weight of 62 pounds per foot, we came up with 2. It only increased our requirement by 2. So we went from needing a plastic section modulus of 125 up to 127. And that was the full 62 pounds per foot amount. So if we're talking less than that, like a sixth of that amount, in increasing from a W21 by 62 to a W21 by 73, obviously this is going to increase our need for plastic section modulus by something less than 2. And so, our total required amount, earlier it was 128. It's now going to be no more than 130, and this is providing 172. So, to make a long story short, we don't need to go through the math again. This increases our self-weight by such a small amount that we can just say that that is good. So plastic section modulus is good. Moment of inertia is good. The only thing left to check is the shear stress. Or actually, instead of calculating the shear stress, the formulas that we have provided for us are in terms of just the shear force, the V, the total amount of shear that is subjected to the beam. And the allowable shear on a steel beam, we are allowed what's considered the yielding stress in shear is 60% or 0.6 of the tensile or compressive yield stress. So 0.6 of Fy times the area of the web, which is what is going to resist the shear. If you recall, when we talked about shear, specifically regarding wide flanges, the flanges don't do much in terms of resisting shear. The overwhelming majority of shear resistance in a wide flange beam comes from the flange. So we can calculate the web. This is the web in the center of the wide flange. And we can calculate the area of that web by multiplying the depth, which is the height of this tall, skinny rectangle, by the thickness of the web. So those two multiplied by each other give us this area. That area is what resists shear. So we're essentially taking stress times area, which gives us the shear force that the beam can resist, and then we are dividing it by another factor of safety. This time the shear factor of safety, so it's omega sub W. Again, because it's a different application, it's a different factor of safety. When it comes to shear, the factor of safety is 1.5 instead of 1.67. So to calculate how much shear this chosen beam can resist, it's going to be 0.6 times the yield stress. Again, the yield stress is based on the material. The material is A992 steel, which has a yield stress of 50 ksi. And the factor of safety is 1.5. What we need to do is figure out what is the area of the web for the beam that we have chosen, a W21 by 73. So that's going to require going back to the appendix one more time. So this time we are going to have to go back to Appendix A. That's the appendix that has the most amount of information on wide flange beams. And the area of the web, as I said, is equal to the depth of the beam multiplied by the thickness of the web. A W21 should be approximately 21 inches deep. And when I look it up in the appendix, I see that a W21 by 73 has an actual depth of 21.2 inches. So you always want to use the precise values found in the appendix. You never want to use just the nominal 21 value, unless you didn't have access to an appendix, I suppose. 21 is approximate, but not precise enough for design work. The thickness of the web of a W21 by 73 is 0.455. So 0.455 inches. And so that gives me an area of 21.2 multiplied by 0.455. That's an area of the web of 9.65. Well, maybe I won't round this one up since it would be more conservative to leave it as the full decimal amount. So I'll make that 9.646 inches squared. I don't think it'll make much difference, but better to be conservative. So that's 9.646 square inches. And so then if I take 0.6 times 50 ksi times 9.646, which is the area of the web, divided by the factor of safety of 1.5, I can see that this beam that we have chosen is capable of resisting 192.92 kips. So I was using kips and inches, so my resulting shear force is in kips. So 192.92 kips is what this is capable of resisting. The question is, how much shear is it actually going to be exposed to? So for that, we can go once again back to Appendix H and look up the maximum shear for a simply supported beam with a uniformly distributed load. The formula is pretty simple. It's just the distributed load times the length divided by 2. And we should include the self-weight in our W. So we did that earlier, right up here when we calculated our moment of inertia we needed. The total distributed load, including the self-weight of the beam. Well, actually, this self-weight was including the when we were going with the smaller beam size, the 0.6, the 62 kip per foot beam. So I suppose we should recalculate this now. So this is going to be our distributed load now is 4.0, and we've gone with what now? 73. So 4.073 kips per foot. And let's convert that to, well, actually, no, we can't just leave that in kips per foot because then we can just put our length in as feet. So we've got 4.073 kips per foot multiplied by 25 feet. And then we're just going to divide that by 2. The feet and feet are going to cancel out, and that's just going to leave us with kips. So we don't need to worry about converting the units here. Forget I even said that. So we've got 4.073 multiplied by 25 foot span length divided by 2, because it's evenly supported by the 2 supports. And the actual amount of shear that this is going to experience is 50.9 kips. So this is actual. This is what it will actually be subjected to, whereas this is its capacity. This is what it's capable of resisting. So we can see that we're not coming anywhere near the shear capacity of this beam. 50.9 kips is only slightly over a quarter of what this beam is capable of resisting. So to summarize here, we are going to use a W21 by 73. We checked that the plastic section modulus is adequate. Check, it is. So it won't be overstressed. We checked that the moment of inertia is adequate. Check, it is. So it won't deflect too much. And we checked the shear capacity of it. The shear capacity of this beam, check, is good enough. So all 3 of those things are good. So that means the W21 by 73 is the beam to choose. Okay, so this is the basic process for designing a steel beam. You find the maximum moment. Based on the maximum moment, choose a beam with an adequately large plastic section modulus. You should include then the self-weight and make sure that the plastic section modulus is still good. Then, including the self-weight, check the moment of inertia. If it's good, then you can check the shear, and it will most likely be good, and you're done. If the moment of inertia is not good, if it needs to be bigger, then you need to choose a bigger beam, as we did in this example. Make sure that the plastic section modulus is still good. It should be, if you're choosing a bigger beam. And then, again, finally check the shear capacity and make sure that's good. If these things are all good, then the chosen beam is good. And that's how you design a steel beam.